Yeah, can you hear me now?
Yeah, we can hear you.
Okay, great.
All right, so we'll get started. Our topic is hydrogen generation. Nathan's online. I'm Brad, and this is Camden. And you might wonder, why would you want to generate hydrogen using optics? Well, I think the biggest thing going for hydrogen is it's got exceptional energy density. As you can see in the table to the right over there, hydrogen in both the gas state and the liquid state have more than double the energy density than conventional gasoline does. So if we can store energy in hydrogen, it has great potential there. Once hydrogen is produced and stored, there's multiple uses for it. You can convert it into electricity. You can use it for cooking or heating at home or water. It's even used for rocket fuel, and there's a lot more applications out there. The potential to have no carbon footprint is huge depending on the way you source and use your hydrogen. When you combust it, water is the only byproduct. Another reason to use hydrogen is to use it as an alternative energy to batteries. A lot of lithium-ion batteries that we use today have a pretty big impact on our environment when it comes to mining and the chemicals and kind of the backlash from that. So we'll talk about a few different ways of generating hydrogen that are used today. We'll go over steam reforming, biomass processing, electrolysis, thermochemical water splitting, and photochemical water splitting. All of these have their pros and cons as we'll go through together. So first is steam reforming. In the US, 95% of hydrogen produced is made by natural gas steam. One of the main components in natural gas is methane that's CH4. And that's the hydrogen is extracted out of the methane in the natural gas. The process requires really high temperatures from 700 degrees C to 1100 degrees C. And instead of using just natural gas, you can use other desulfurized hydrocarbon gases as well. But natural gas is the primary source in most applications.
Does natural gas need to be pre-refined before sending it?
I don't know. I would assume so, but you know what they say about making assumptions. Yeah. So when you steam reform, most of the time, there's two processes. First, you go through a steam methane reforming process, and then you go through a water gas shift reaction. Both of the processes produce hydrogen. The second process is it just gets more hydrogen out of the system. And as you can see, it takes...
What do you mean the second process produces more hydrogen?
It produces additional hydrogen. It doesn't produce...
Am I missing something?
So you're taking the CO?
Yeah, you're taking the CO and you're using the CO to create CO2 and more hydrogen. Yes. Yeah, no problem. So in this diagram that we found, you put in energy, heat, 2.2 tons of methane and 4.9 tons of water creates 1.1 ton of hydrogen. But the downside to steam reforming is it creates all of the CO2, which isn't too good for our environment. Some of the pros to steam reforming is it's very cost effective. It's the most cost effective solution that we found at about 75 cents per kilogram. It's scalable. It's like a big industrial thing. So you can create a lot of hydrogen as long as you have enough natural gas. And it uses readily available sources. You don't have to go mining for any crazy elements or anything like that. The cons is it produces quite a bit of carbon emissions. It consumes non-renewable energy, and it requires a lot of heat energy to extract the hydrogen out of the natural gas. And then storage and transportation once the hydrogen is produced is a pretty big problem as well when you're manufacturing it in scale, because hydrogen is like one of the smallest atoms. Well, it is the smallest. And it leaches through like a lot of containers that you make for it.
Does the cost include the energy cost? Because if in the previous slide, it's pretty clear that it much of energy.
Yeah, I think it does.
Probably.
Yeah. All right.
And the output is gas.
Yes. So next up is biomass. This is relatively in research phase. It's not used on large scale yet. Biomass is a renewable organic resource, such as agriculture crop, forest residues, special crops grown specifically for energy use, organic solid waste and animal waste, and more. There's three main processes that use biomass to create hydrogen. The first one, well, the first two, I won't cover too much in depth as they're fairly in research. The first one is mainly just using algae. It's a special algae that has been created to turn biomass into renewable energies, and one of those is hydrogen. It's very research phase. It's not very cost productive, and there's not a lot of use with it right now. It needs more research. The second one is electrochemical. Yeah, it can be made quite cheaply. It just needs more research to in that area. It's not too used right now. Electrochemical, I won't talk about it as much as Nathan will go over this more with his, but it uses electrolysis to do this, except instead of water, it's biomass. And it's not as useful as water is. The third one is thermochemical. That's the primary way that we use biomass currently. It's the most developed way, but like steam reforming, it also takes very high temperatures. As you can see, it's over 1,000 degrees Celsius for gasification specifically. These other two don't take as high of temperatures, but they still require temperature or pressure to be built. Gasification, here's the chemical formula. You can see biomass plus air equals all this other stuff, and this is what we're mainly going for. As you saw in the steam reforming, you could take the CO and further develop more hydrogen with that. A cool part about pyrolysis is this already exists in the market. We build charcoal using this. So this is already in field, already being used. We're just not harvesting the hydrogen currently. We're just mainly using it for the charcoal.
And what's the difference between those two? Is it just that pyrolysis just requires much air?
So gasification is oxygen deficient, whereas pyrolysis isn't.
So you still need air there on the left-hand side of pyrolysis?
Or maybe I have them mixed up. I believe actually pyrolysis is oxygen deficient. Gasification has oxygen. Yes. So here's, I guess, the flow chart of gasification. So biomass plus gas into gasification. It has its byproducts, tar and char, as well as these other gases. And then you have the steam reforming that Brad was talking about that further gives more H2 and CO2. The pros and cons is biomass is a very abundant resource. It's used domestically, on farms, animals. It's very widely available. And the CO2 that was emitted is recycled because now you're farming with plants that then take that CO2 out of the air. So instead of, the steam reforming that Brad talked about that produces the CO2, it produces the same amount of CO2, but then it gets reused in the plants, in the algae, in the biomass itself. The cons is it's very high cost compared to steam reduction. You're talking almost 3 times the cost per kilogram of hydrogen. And that mainly just comes from the infrastructure. Infrastructure is not built
currently to create biomass and hydrogen.
What do you mean by the infrastructure? I didn't get.
So like our farming practices right now, we don't care. We're just releasing the hydrogen into the atmosphere, and we don't care about it.
So you're saying there is no standardized procedure to capture?
No, there's no, and that's one of the biggest costs is you have to separate the oxygen from ambient air as well as the hydrogen gas from the other gases that are produced, which has high cost involved in the filters and high heat or energy usage, and the tars that were formed can slow the process down. The biomass cost, again, it's widely available, but our farming practices, our current farming techniques, and immediate access / transportation is limited in that, and that accounts partly for the high cost.
All right, Nathan, you're up.
So yeah, I'll take over the electrolysis part from here. So the two methods we've talked about up until now are both using more complex stock, whether that's fossil fuels or biomass. Electrolysis has benefits in that you're really just splitting water, which is incredibly abundant on the planet. It covers what, like 70% of the planet. And when you react the hydrogen, when you burn the hydrogen, you just get water back. So it's a closed loop with no net emissions at all, potentially. However, if ever the energy cost it takes to split an atom to split water is actually very high. So electrolysis systems tend to have two main components. One is they'll need to lower some sort of catalyst that lowers the amount of energy you need to break the water into oxygen and hydrogen. And secondly, some ability to separate the oxygen and hydrogen so they don't recombine, and so you get them in pure forms. As I said, the pros to this method is that the feedstock is water, and you get water back. So it's completely carbon-free, potentially, depending on your energy source. The cons for this method, it can vary a lot. The government's target price for hydrogen production is less than $2 per kilogram. At the cheapest, it can be pretty close to that, $2.17, but it can go as high as like $20 a kilogram, which is currently just not economically viable. And sort of combined with that, it's cheapest when you do it in a nuclear facility. It's sort of a byproduct of nuclear energy production. But it's been a long time since America's really invested a ton in nuclear. That might change, but as of now, that really limits where this can be done. And the most expensive options are with wind and solar, which would be the more, the more truly green methods and the methods that can be deployed all over the country. And so that's a drawback as well. Go to the next slide. So far what we've talked about are more like current solutions and midterm solutions. There's a couple things that are viewed as sort of long-term solutions that could potentially, these are better methods but the technology is still in development. Thermochemical water splitting is one. If you look at this diagram I've got on the right, these are two options for solar collectors. So think of those little squares or that semicircle as mirrors that are reflecting and concentrating sunlight towards a reaction center, towards a reactor. So in this method, essentially you have a bunch of sunlight, or you can also use nuclear energy to concentrate energy onto a reactor where you have water, and then it splits that out. Ideally, this is a closed loop reaction. So even though there are intermediate steps, all those steps end up being reversed as well. So the only thing that really goes in is heat, and the only thing that and heat and water, and the only thing that comes out is oxygen and hydrogen. The ones in the middle should be able to just be reused indefinitely. Pros to this are, as I said, it can be reused, or the intermediate compounds can be reused, so it's very passive. Heat and water are the only inputs, and you don't need any sort of carefully designed membrane to separate the components. Cons are that it's still very much in development. I think I found something like 5 or 6 of the most promising out of like so many different potential methods to do this, but it's definitely something that's been done more on a research scale, not a production scale. So one of the factors they're worrying about is improving the stability and efficiency of the intermediate reactions, the reactions that you do between water and hydrogen and oxygen. There's also a really high capital investment if you use the solar concentrator method. These fancy mirrors can cost quite a bit. And so if we look at the costs, we're rising in costs now. Minimum cost is around $4.55, and then going up into more than $10 per kilogram of hydrogen created. Next slide. In the extreme long term, there's photochemical water splitting. I don't know, people, maybe you'll even remember those old calculators anymore that used to have those little solar chips on them. But these are constructed very similarly to that. You essentially have a semiconductor with an electrolyte, that's water-based electrolyte on top of that special semiconductor. And you put that out in the sun like a solar cell or like a solar panel. Energy will hit the electrolyte, the sunlight will absorb the energy, and the substrate will catalyze reactions that split the hydrogen. And it's, as I said, it's similar to electrolyte solar panels like what used to be in calculators. As far as pros, very long term, it's very promising in the long term. It has the potential to be extremely high efficiency and with a very low cost of materials. Typically, the substrate is very common material. Like I've seen ones with iron oxide or titanium oxide, stuff like that. And it's also very scalable. You could deploy this, since it's the size of a solar panel, very easily with minimum, you don't need a big supply chain or anything. Cons, currently it's still extremely expensive in the research phase that it's at. Minimum cost is over $8 per kilogram, and the technology is just not yet ready. They need to work harder to get better catalysts and better efficiency, and also to have them be durable enough that their lifetime is long enough to recoup your costs. And that's all.
We're excited. Questions?
I did ask all my questions, and you guys went a bit over, so we should talk. Thank you.
All right.
What's next?